You ever just look up at that big blue sky and think about what's really holding it there? I mean, we've got this thin blanket of air that keeps us all alive, and right on the other side is the vacuum of space. So how on earth has it stuck around for billions of years? Well, that's exactly what we're going to dig into.
It really is a great question, isn't it? It feels like it should be simple, but it's one of the most fundamental questions for all life on this planet. Why doesn't our atmosphere just, wander off? What's keeping it here day in and day out?
And yeah, the first thing that pops into your head is probably gravity, and you're not wrong. On the most basic level, Earth's immense gravitational pull is what holds all those gas molecules close. It's like a giant cosmic security blanket.
But wait a second. If it were that simple, what about Mars? Mars has gravity, right? But its atmosphere is mostly gone, stripped away over time. So clearly, gravity can't be the whole story. There's got to be more to it. So, let's peel back the layers and see what's really going on.
To really get this, you have to picture it as a constant battle, a cosmic tug-of-war. On one side, you have the planet, desperately trying to hold on to its air. And on the other, you have every single gas molecule with this unending urge to just escape into the void.
The main weapon in the planet's arsenal is gravity, and we can measure its power with something called escape velocity. The best way to think about it is like a speed limit for leaving the planet. If you can move faster than that speed, you're gone, you're free. Anything slower, and gravity just yanks you right back down.
And here on Earth, that magic number is a wild 11.2 kilometers per second. Okay, that's over 40,000 kilometers an hour. So for a tiny, tiny little gas molecule to break free, it has to be moving at an absolutely incredible speed.
But here's the thing. Not all gases are created equal. Up in the atmosphere, heat gives them energy, making them zip around like crazy. The lighter gases, like hydrogen and helium, they're the nimble escape artists. They're so light they can get up to those crazy speeds much more easily. But the heavyweights in our air, the nitrogen and oxygen we breathe, they're the homebodies. They're just too big and sluggish to really get going fast enough.
And make no mistake, Earth is losing gas. We're leaking about 3 kilograms of hydrogen, that's like a couple of laptops worth, into space every single second. But before you panic, our entire atmosphere weighs around 5 quintillion kilograms. That number is so big, it's hard to even picture. It's like more than a billion Great Pyramids of Giza. So the amount we're losing, it's a tiny, tiny drop in an enormous bucket. It's a leak, sure, but a very, very slow one.
So, okay, gravity is kind of like the big bouncer at the club door, keeping most everyone inside. But it's not working alone. Earth has this whole multi-layered security system that makes it even tougher for gases to just leave the party.
For a molecule to escape, it has to run this incredible gauntlet. First, down in the lower layers, it's super dense, so it's constantly bumping into other molecules, which slows it down. Then, if it gets past that, it hits something called the cold trap. This is this brutally cold layer that freezes any water vapor, making it fall back down. And that is so important because if water vapor got higher, sunlight would just split it apart and we'd lose all that light hydrogen way faster. Only after all of that can a molecule finally make it to the exosphere, the last stop, where it even has a chance to escape.
Okay, so this is where a lot of us probably remember something from school about the magnetic field, right? That it's this big hero, this shield that protects us from the solar wind that would just blow our atmosphere away. And yeah, it definitely helps, but is it really the main reason we're all still here breathing?
Well, this is where it gets really interesting. Recent studies and simulations are showing that even if you could just switch off Earth's magnetic field, our planet's gravity is so powerful that it would still hang on to almost all of our air for 1 billion years. The magnetic field is a nice bonus for sure, but it's not the ultimate savior we thought it was. Gravity really is the heavyweight champion here.
But here's the other half of the story. Because just holding on to what you have is a defensive game. Earth plays offense too. It's not just some static container with a slow leak. It's a living, breathing system that actively tops itself up.
Think about it. Our planet is constantly refreshing its own air. You've got volcanoes burping up gases from deep inside the Earth's mantle. You have life itself, photosynthesis, managing all the oxygen and CO2. And then you have these huge, slow geological cycles and ocean currents that are constantly recycling key elements, making sure the whole system stays in balance.
So when you put all of that together, the super strong gravity, the layered defense system, and this constant replenishment, you start to get a picture of just how special our situation is. Let's kind of zoom out now and see how we stack up against our neighbors. And this table really tells the story. You look at Mars, it's just too small. Its gravity is too weak, and its atmosphere got blasted away.
Then there's Venus, almost our twin in size. But with no magnetic field and that insane heat, it held onto its heavy gases, sure, but that led to a runaway greenhouse nightmare. Earth has the trifecta. We're the right size, at the right temperature, with a living, active geology. In fact, scientists who hunt for planets have this really cool name for this idea. They call it the cosmic shoreline. It's basically a line you can draw based on a planet's size and how much energy it's getting from its star. If a planet falls below that line, well, it's pretty likely its atmosphere has been stripped bare.
And that's the whole thing, right? Our world exists in this perfect, delicate balance. We're sitting right in that sweet spot, just on the safe side of that cosmic shoreline, in a little harbor where an atmosphere and life itself can actually thrive. It's not just one thing. It's this beautiful, complex recipe that keeps our sky right where it belongs.
And that, of course, leaves us with one final, incredible thought. We've got a pretty good handle now on why our atmosphere is here to stay. But as we look out into the cosmos, at all those countless worlds out there, the real question is, how many of them are also sitting in that sweet spot, just waiting for us to find them?